Continue on Physical Chemistry, Chapter 2. We're beginning Section 7 now. So we talked in the last section about internal pressure, but how do we measure internal pressure for gases? Now remember, we said internal pressure is the partial derivative of the internal energy with respect to volume holding temperature constant. Now Joule did an experiment somewhere around 1842 or 1843. Now this is a diagram of the experiment. We have water here. We have a couple of containers here connected together. Container A has a gas in it. Container V has a vacuum in it, and there's a plug in between. Now the walls out here are adiabatic, so we're going to say Q is equal to 0. Then we got a thermometer in here, so we can monitor the temperature. Now, the gas, since this is a vacuum, all our gas started over here. So we're going to say it had a pressure, a volume, and a temperature. Since it was the initial temperature and pressure and volume, we'll say it's just pressure 1, P1, volume 1, V1, and temperature 1, T1. Now, what he started was with a pressure of 22 atmospheres. Remember, you're breathing 1 atmosphere, so this is higher pressure than you're used to. So he opened up the plug and he let the gas expand into the vacuum. So remember, then the volume of the gas increased because the volume was this big originally, but then it was this big before or after. So the final volume would be our initial volume, V1, plus the volume of this B container. I mean, that would include everything in the middle too, of course. But now remember, differential of reversible work is minus PdV. That does not apply to this situation because this situation is not reversible. This is reversible work. This is an irreversible process. So we're actually going to say the differential of work is equal to 0. Why? Because this gas is expanding into a vacuum. It's not being held by any force. The force is 0. So I mean, it's that simple. If work is force times distance, 0 force times whatever distance is 0. So like I said, this plug in here, or a stopper, it opens it up, and then we end up with pressure 2, pressure at state 2, V2, volume at state 2, and T2, temperature at state 2. Now the change in internal energy is always Q plus W. Now we said it's adiabatic, so Q has to be 0. And we said the work has to be 0. Therefore, the change in internal energy is equal to 0. So that means U2 minus U1 is equal to 0. The internal energy at state 2 minus the internal energy at state 1 is equal to 0. Therefore, we can say that the internal energy at state 2 is equal to the internal energy at state 1. So when Joule did this experiment, he saw no difference. So he concluded that the partial derivative of internal energy with respect to volume at constant temperature is equal to 0. Now remember, we're going to say internal energy is a function of temperature and volume. So the differential, writing out the exact differential, we get the differential of internal energy is the partial derivative of U with respect to volume holding temperature constant times dV, plus the partial derivative of internal energy with respect to temperature holding volume constant times dt. Now, based on what Joule saw, we're going to say du is equal to 0. And we also know that the partial derivative of U with respect to T holding V constant dt is equal to 0. But we know that this differential here is not equal to 0. The volume did increase. Now, remember though, Joule's experiment was limited. This partial derivative of U with respect to volume holding temperature constant, that is actually equal to 0 for an ideal gas because there are no intermolecular attractions. For real gas, it is actually going to be non-zero. Now, we're going to have mu subscript capital J to mean the Joule coefficient. We're going to define mu sub J, the Joule coefficient, as the partial derivative of temperature with respect to volume holding internal energy constant. So, how do we compare the partial derivative of temperature with respect to volume holding internal energy constant with the partial derivative of internal energy with respect to volume holding temperature constant? Well, hopefully if you've taken multivariate calculus, you remember the Euler relation. So let's say that we have some arbitrary variable z that's a function of other variables x and y. Remember, show a circle like this, x, y, z. To do this, the partial derivative of x with respect to y holding z constant times the partial derivative of y with respect to z holding x constant times the partial derivative of z with respect to x holding y constant is equal to -1. So likewise, instead of x, y, z, we have internal energy is a function of temperature and volume. So we know that the partial derivative of temperature with respect to internal energy holding volume constant times the partial derivative of internal energy with respect to volume holding temperature constant times the partial derivative of volume with respect to temperature holding internal energy constant has got to be equal to -1 based on the Euler relation. So doing the algebra, we end up with the partial derivative of internal energy with respect to volume holding temperature constant is equal to -1 over the partial derivative of temperature with respect to internal energy holding volume constant times the partial derivative of volume with respect to temperature holding internal energy constant. So because they're in the denominators, we can just flip those right side up. So we get that equals to minus partial derivative of internal energy with respect to temperature holding volume constant times the partial derivative of temperature with respect to volume holding internal energy constant. And that is equal to the heat capacity at constant volume times mu J, the Joule coefficient. Now, like I said before, mu J is equal to 0 when you have an ideal gas or perfect gas only. Later on, we'll talk about what the difference is between a perfect gas and ideal gas, and it turns out there isn't any. And then mu J is equal to 0 since the derivative of the internal energy with respect to volume holding temperature constant is equal to 0. And the heat capacity at constant volume is not equal to 0. See, yeah. Okay, so now let's talk about an updated version of the experiment. The Joule-Thomson experiment, or the Kelvin-Joule experiment. Remember, Lord Kelvin's real name was something Thomson. So this was also in 1853, so over 150 years ago. Now this one's more important than the Joule experiment. So we had a tube here with adiabatic walls. So this is like a really long, cylinder or something. So you have two pistons in it. You have piston 1 over here, and you got a pressure 1. I didn't really show an arrow, but I guess you don't have to. But yeah, there's a pressure over here. And then you have n moles of substance. This dotted line is a force valve or a throttling valve, and this is in a fixed position. And on the other side of this valve, you have a piston with pressure 2. Now what we want to do is calculate the work on each side. So what they did was they pushed in piston 1 on the left, and then that forced piston 2 out slowly. So they did it really, really slow, trying to do it reversibly. We want a reversible process because that's the kind we're qualified to do math on. So remember, we're talking about the work on the left is the work done on the gas, which is our system. So the work on the left, remember, we're constant pressure roughly, is minus PdV. So we get minus P1 times minus V, 0 minus V1. Remember, final minus initial. So final volume is 0 because there won't be any volume on the left side anymore. We're pushing all the gas to the right side, the other piston. So double negative multiplied equals positive P1 V1. So the work done on the gas on the left side is positive. Now on the right side, the work is being done by the gas to push the piston. So the work on the right side is equal to minus P dV. The final volume is going to be positive because it's expanding. The initial volume was 0 because all the gas started on the left side. So this time, notice there's no negative sign. I mean, it's going to end up negative. So the work on the right side is going to be minus pressure 2 times volume 2. So we end up with negative work because the work is being done by the system, our gas. Now Q should be 0 because we did this adiabatically. Remember I said the cylinder or whatever, the pistons were all adiabatic. So delta U, the change in internal energy, should be the net work by the first law of thermodynamics, conservation of energy. So the net work is going to be equal to pressure 1 times volume 1 minus pressure 2 times volume 2, which is going to be equal to the internal energy at state 2 minus the internal energy at state 1. So just moving the 1's to one side and the 2's to the other, we're going to get U plus P1V1 is equal to U2 plus P2V2. Now remember, we defined enthalpy as U plus PV. Therefore, we have the enthalpy at side 1, state 1, is equal to enthalpy at state 2. So what this says is that the Joule-Thomson experiment is constant enthalpy. The change in enthalpy is equal to 0. Now let's define another coefficient, mu sub jt. That's a capital J subscript, capital T subscript. So mu jt is defined as the partial derivative of temperature with respect to pressure, holding enthalpy constant. Now this is a measurable quantity. Now it can be plus or minus. It can be like, up to 3 degrees Celsius per atmosphere. It can be like negative 0.1 degrees Celsius per atmosphere, or in between. In some rare circumstances, you might even be able to find it 0. I don't know. So it depends on the gas, and it depends on what conditions. Because remember, this is dependent on intermolecular forces. This is actually what they use to cool or liquefy gases. By, letting the gas expand, it cools and so on. So mu jt is dependent on temperature and pressure, but it is substance specific too. Now positive mu jt means that the gas will cool when it expands. So a negative jt means the gas will actually warm up when it expands. Enthalpy is constant in the Joule-Thomson experiment. We said that before. But temperature, volume, pressure, and internal energy, those are all changing in a Joule-Thomson experiment. Now remember, these are all state variables, but they can change because this isn't a cyclic process. So don't misapply what we learned before. Like, don't apply what you learned about a cyclic process to this, because we didn't do a cyclic process. We just went one way, not both ways. Now, if you just do the Joule-Thomson experiment once, you get a finite change. You get the change in temperature, delta T, divided by the change in pressure, delta P, at constant enthalpy. Now, what you can do is you repeat it with different starting pressures. So you end up with like P1 T1 to P2 T2 with P1 greater than P2. And then you go from P1 T1 to P3 T3 with P1 greater than P2 and P3 not equal to P2. So you just repeat it with different conditions, and you connect all those points. So here we have a graph of temperature versus pressure. So you connect all those points and you make a curve. Now over here, mu jt is greater than 0, which means the temperature, it's going to increase with increasing pressure, or it's going to cool when it expands. See, or wait, I got that backwards. It's going to cool when you compress it. Remember, oh boy. Yeah, less pressure. This is lower pressure, so it's expanding. So if decreasing pressure means it's expanding, and the temperature will actually decrease when it's expanding. So over here, the pressure is increasing, so we're compressing it, so the temperature is going back down when we compress it. So over here, mu jt is less than 0. There is, of course, one point where mu jt happens to be equal to 0, which means you change the pressure by a finite amount and the temperature doesn't change. Of course, this is probably a narrow, infinitely small point, infinitesimal. So this curve of connecting all those points of constant enthalpy, that'd be isenthalpic curve, which means H is constant. So this is 1 isenthalp. Now, where this special point here, where mu jt is equal to 0, that's called the inversion point, or the inversion temperature. Every gas has an inversion temperature. Well, every real gas, of course. Ideal gases, maybe not so much. Now, what you can do then, repeat the Joule-Thomson experiment, but with different initial pressure, and you can generate other isenthalpic curves. So you're doing the experiment a bunch of times here with one starting pressure, did the etc., etc., etc. You just keep doing that, and you get all these. So then you can connect the dots of all these to make a new curve or whatever. So like I said, when mu JT is equal to 0, if you allow the gas to expand, it's not going to heat up or cool down. So this actually has practical uses in real life. If you do an adiabatic expansion of a gas where the it's set to the mu JT is less than 0, you know, the right temperature and pressure for mu JT to be less than 0, well, it's going to cool down, right? Therefore, you can actually liquefy it. An ideal gas, it won't liquefy. But real gas, eventually, you get cool enough, you just turn into a liquid. And of course, most of the time when you're doing stuff like that in a chiller or whatever, you want to cool the gas. The engineer's designing the system to cool the gas. Like I said, to condense it to liquid or whatever. You know, we already showed that enthalpy is a function of temperature and pressure. So the exact differential is going to be the differential of enthalpy is the partial derivative of enthalpy with respect to temperature holding pressure constant times the differential of temperature plus the partial derivative of enthalpy with respect to pressure holding temperature constant times the differential of pressure. This here is called the slope formula. So this here is the slope at constant pressure. This here is the slope at constant pressure. This will be called mu t on the handout. I forgot to write the number of the handout, darn it. Okay, the partial derivative of enthalpy with respect to pressure holding temperature constant, that's equal to minus the heat capacity at pressure at constant pressure times mu jt, which on the handout is just called mu t, the constant temperature. So axes, we would have 3 dimensions then if we wanted to graph that: enthalpy, pressure, and temperature. So look at handout figure 7. Now let's talk about what happened with the British petroleum oil rig that happened a few years ago. So remember, in the Gulf of Mexico, on the seafloor is like 5,000 feet below the surface of the ocean. Now, we know that the density of water is about 1.03 grams per milliliter. That's salt water, because remember it has ions dissolved in it, etc. So that's 1,030 kilograms per cubic meter. Now, the pressure is just rho GH. Hopefully you remember that from chemistry. It's still true. So we have 1,030 kilograms per meter cubed times 9.8 meters per second squared times 1,524 meters, that's the depth, or height, whatever you want to call it. So that gives us 1.54 times 10 to the 7 pascals, which is 152 atmospheres. Now the pressure of the oil or the gas coming out of that leak was roughly 460 atmospheres. So the change in pressure when it leaked out into the ocean is actually a great decrease. Now remember, it was officially an oil rig, but a lot of times with oil you have natural gas, which, methane, ethane, and propane, I think, is the next one. So the change in pressure would be, P2 minus P1, so 152 atmosphere minus 460 atmospheres. So the pressure decreased by 308 atmospheres. Now the initial temperature at the bottom of the ocean, at least the water, is 5 degrees Celsius. I would assume that the oil and natural gas were about the same temperature. Now water is actually the highest density at about 4 degrees Celsius. That's why the bottom of the ocean is so cold, given the chance. So mu JT, we're going to say, is 0.265 kelvins per atmosphere. Now remember, mu JT is the partial derivative of temperature with respect to pressure holding enthalpy constant. We're going to be just lazy and not do any calculus and say, okay, it's delta temperature over delta pressure divided by enthalpy. So that solve for delta T, we get delta T is roughly equal to mu JT times the change in pressure. So we just take 0.265 kelvins per atmospheres times negative 380 atmospheres, and we're going to say, okay, that oil natural gas mixture and the water itself cooled down by about negative 81.6 kelvins. So the temperature too, it's just the initial temperature plus the change in temperature. So we're going to say, okay, so it was roughly freezing, 278 kelvins, plus negative 81.6 kelvins. That's going to be equal to 196.4 kelvins, or negative 76.6 degrees Celsius. So what that means is the water froze. Okay, that is all for Chapter 2, Section 6.